Right, so welcome to the first video on the rational numbers. And this is going to be actually a long series of videos because there's a lot of things that we need to learn about the rationals that are quite important to some of the stuff that we're going to be dealing with here, especially in the topic of financial calculations. So I guess the first starting point for us is going to be to define what rational numbers actually are. So we're going to begin by talking about the real numbers, which are essentially all the numbers that are from minus infinity. So they go minus 3, minus 2, minus 1, 0, 1, 2. So all of those, which are essentially all the integers, but they also contain pretty much any number in between the integers. So we could have fractions like minus 3.57. Here we could have something like minus 1.75, and we could even have numbers that have an infinite number of decimal places. So the real numbers pretty much encapsulate all of these different types of numbers, but they can be broken down into two very special sets. So the first one is called the rationals, and by rational, which we essentially mean just any number that can be expressed as a fraction. So something like 48 on 6. Now we know that 48 divided by 6, that's actually going to be 8. So essentially what we have here is we have rational numbers that can also be considered as whole numbers. So a whole number can be a rational if we express it as an improper fraction like this one. So I guess there's really not a massive distinction between rationals and whole numbers when it comes to these cases, but the rational numbers are more general because they cover things that do not really simplify to a whole number but must be expressed as fractions. So to give you an example, 1 over 2, that's going to be 0.5. There's no way we can express this as a whole number, so it has to stay just as 0.5. Now rational numbers are defined by two different types. So the first type is a terminating decimal. So a terminating decimal would be something like this one and that one. And essentially what that means is that, for example, this one, it doesn't really have any decimal places, but if we wanted to, we could just write 8.0 and it would be the same as 8. So it means that the decimals just have a finite number. They don't continue to infinity, but rather it has a finite number of decimal places. The same situation happens with this one. You have 0.5 and it only has one decimal place. There's nothing after this. I mean, there's a bunch of zeros, but we don't really count those. So we say that it only has one decimal place. So other types of examples would be 1.2, 2.25, and pretty much any number that has a finite number of decimal places. Now there is another type of rational number, and this one is quite interesting because it has an infinite number of decimal places. So an example of that would be in this case something like 0.5. Now this little dot on top of the 5, what it actually means is that we have a number like this that is going to continue all the way to infinity. This 5 is just essentially being repeated all the way to infinity, and you can imagine that this thing is never actually going to end. This number, even though it's quite small because it's actually close to half, it still has an infinite number of decimal places. So you can imagine it would be quite a nightmare trying to round this to a certain number of decimal places. I mean, we could do it for the first few, of course, but if we wanted to go very, very adventurous with it and say, let's round it to 100 decimal places, well, we would have to count 100 fives in those decimal places and then round it up. But basically, this is essentially what it means. So if you ever see a decimal that has something like a dot on top of it, what it essentially means is that same digit, that same number is going to be the digit that follows after all the way to infinity. So this is actually going to continue like that. And this is still considered a rational number. So that's a very important distinction that we need to make. And the reason for that is going to become apparent in a few minutes when I actually talk about irrationals and some types of fractions and rational numbers. but this is pretty much what we need to be aware of. So another example would be, of course, minus 1.4. This essentially means that the 4 here is going to be repeated. So we're going to have the following number, minus 1.4, 4, 4, and then the 4 is going to repeat all the way to infinity. So we have an infinite number of decimal places. Another type of recurring decimal that you can have is something that has more than one digit that is repeating itself. So in this case, we have 2.35, and there's a straight bar on top of those two numbers. What that means is that we're essentially going to repeat the same sequence of numbers. So we're going to take in both the 3 and 5 as a single number, in this case 35, and that's the number that we're going to repeat in the sequence. So in this case, if we wanted to write this down in a more explicit way, we would write it as 2.35, 35, 35, and then it just continues like that. So you can see that the same pattern of the 3 and the 5 is going to get repeated. And this is basically what that bar on top means. And you can have any combination of these things. So you could have a number that has a bunch of decimals, and then the last decimal has a dot on top of it, which means that all the following decimals are going to be that one number. Or you could just have something that ends in something like this. So those are still considered rational numbers. Now, moving on to the irrationals. This is a little bit more complex because irrational numbers are very strange. So they usually have an infinite number of decimal places. They cannot be expressed as a simple fraction like this. So let's say a simple fraction would be something like 7 on 5 or even 1 on 3. So to give you an example of that, 1 on 3 would be something like 0.333 and so on. So it has an infinite number of decimal places because the 3 is being repeated all the way to infinity. But it is still expressed as a single fraction, so this is still a rational number. However, an irrational number can never be expressed as a fraction like this. So an example of that would be the square root of 2. Because if you plug that into your calculator, you will find that it has a bunch of digits and it doesn't actually end, but because the calculator is limited, it is only going to show you a certain number of digits before it actually stops counting. But in essence, this number has an infinite number of decimal places. The difference is, what makes this number irrational is that those digits do not follow any predictable pattern. They're actually just occurring at random. So unlike the examples that we saw here with recurring decimals, an irrational number like the square root of 2 has an infinite number of decimal places, but the numbers do not actually follow any pattern. So you will never see repetition like this where you can just compress it or compact it down to a very nice notation like that. So this is why we call it an irrational. Another example of that would be the number pi. We know that pi has a value of 3.14159, and then it continues off like that. And it just has a random arrangement of digits. After that, it goes to infinity. So because we cannot really express this as a fraction, and because it is a non-recurring, it is a recurring decimal, but it does not follow any pattern that we can predict, then we call it an irrational number. And in fact, pi in itself is a very special number because not only is it irrational, but it is also something called a transcendental number. Let me see if I spelled this right. So transcendental. Now the concept of a transcendental number is a little bit more advanced. I'm not going to go into detail here, but at least I'm going to tell you that transcendental means that it goes beyond what irrational means. So not only is it not expressed as a fraction, but it cannot be expressed as something like a root or a power or simply any other operation you can perform in a number. So that's what it means by transcendental. It is so special that you cannot even express it as something like a square root or a cube root or anything like that. So this is something that pi is. It's a very special number. And in fact, whole studies in mathematics have gone into basically just what the properties of pi are and how to even define pi in the first place. So It's very interesting stuff that people have done when researching this kind of thing. So hopefully that has given you a better idea of what rational numbers are. And now I think it's a good time to just talk about some classifications of fractions, because we're going to be dealing with this quite a lot. We don't really need to know the theory behind this, but at least we need to understand the differences. And at this point, we can actually talk a little bit more about how fractions are classified. So there are three main classifications for a fraction. The first one is a proper fraction, which is essentially some integer a divided by some integer b, in the case when a is less than b. So if the numerator is lower than the denominator, we call that a proper fraction. And an example of that would be something like 2 divided by 7. So what that means is that this fraction is always going to be less than 1. So a proper fraction is one that is smaller than 1, essentially. An improper fraction is one that is still expressed as an integer divided by another integer, but the numerator is greater than the denominator. So by definition, the improper fraction will always be greater than 1. So an example would be 10 on 3. And apart from those two, we can also have something called a mixed number. This is not as common, but it is still used in some places. And it is essentially just the combination of a whole number with a fraction. So an example of that would be 2 and 3/5. So it looks a little bit strange, but this is useful in certain areas. So when you're talking about proportions or things like volumes or areas, or you're comparing the size of an object to another object, this can actually come in quite handy because it is used in measurement quite a lot. So what it means is that you have 2 units of a certain measurement. So this is 1 unit, that's 2 already. And then instead of completing another unit, you're only going to take 3 parts of 5. So you're going to divide this one here into 5 equally spaced measurements or units. And then you're going to fill out 3 of them. So you're going to take 3 portions out of 5. So if you add up this whole portion plus that whole portion plus this portion here, you're going to get 2 and 3/5. So it is not quite 3 units, but it is larger than 2 units. So that, I guess that's the best way that I can explain that concept to you. So this is something that we're going to deal with a little bit more. And there are very nice tricks that can be done to convert this back to something like an improper fraction, or going from an improper fraction to a mixed number. And those are some of the things that we're going to discuss in the next set of videos.